All right. This problem says an aluminum spherical ball of radius 4 centimeters is charged with 5 microcoulombs of charge. Okay, so anytime you throw a bunch of charges on a conductor, we know that it resides on the surface. Okay. A copper spherical shell of inner radius 6 centimeters and outer radius 8 centimeters surrounds it. A total charge of minus 8 microcoulomb is put on the copper shell. Find the electric field at all points in space, including points inside the aluminum and copper shell. Aluminum ball and copper shell. When the copper shell and the sphere are concentric. Okay, so here's the aluminum shell. Aluminum ball, and okay. Now there's 5 microcoulombs of charge on the aluminum ball. So, and you saw that all the charge will reside on the surface. And since this is a sphere, if you look at your notes, this is an equipotential surface and all the charge will evenly distribute, okay, on this conductor. Only on sharp surfaces does more charge collect. On a spherical surface, the charge evenly distributes. Okay, so that's 5 microcoulombs. And this was 4 centimeters. This is 6 centimeters. And this is 8 centimeters. Okay. Now there's a total of minus 8 microcoulombs on the outer shell. There's a total of minus 8 microcoulombs on the outer shell. And what happens is, what you want is the electric field inside the shell to be 0. And for that to happen, what happens is, here's how the charge distributes. You get minus 5 microcoulombs in the inner part and minus 3 microcoulombs on the outer shell, on the outer surface. So here's minus 5 microcoulomb and minus 3 microcoulomb. So that's how the charge distributes. Okay. And the driving principle is, this is an equipotential surface. Here all the charges distributed equally. Electric field inside here is 0. Electric field inside here is 0. Okay. And all those will drive the charges to be distributed like so. Okay. All right. Now we'll find what they're asking us to do is find the electric field at all points in space. They want us to find the electric field here, 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 and here. Okay. We already have the electric field here. Inside is 0. So we have to find the electric field for R between 4 and 6 centimeters. We have the electric field here, and then we have to find the electric field for that region, for R greater than 8 centimeters. Okay. All right. So for part A, (6 and 8 centimeters) and R less than 4 centimeters. Okay. So now we have to find the electric field for R. So for this, what we'll do is we'll draw a Gaussian surface like that. Okay, and I don't want to make the diagram too busy. And from the symmetry of the problem, okay, well, I'll go ahead and draw it. So here's the Gaussian surface. the electric field will be pointing away. And so the flux, which is given by that, is equal to charge inside divided by epsilon naught. Okay. And so this integral is just equal to the electric field times the surface area of a sphere, which is 4 pi r square, equal to q inside divided by epsilon naught. And E is 1 over 4 pi epsilon naught q inside over r square. Okay, and 1 over 4 pi epsilon naught is k, the Coulomb's constant. So for r between the shell and the solid sphere, E is k q inside divided by epsilon naught. So the electric field is as if this was a point charge, and the electric field is just that of a point charge. The point charge at the center. So the electric field is just that, and that's what this thing is saying. Okay. All right. So again, let me summarize this. The electric field inside here is 0 because that's a conductor. The electric field in this gap is as if this were a point charge, and none of these charge influence the electric field there. The electric field here is 0, and the electric field outside, so let's calculate that, and that's the last part. And again, for that, we'll draw this Gaussian surface. I won't draw the whole surface. There's E. Okay. So now we're doing for R greater than 8 centimeters. So that's the only part that's left. And E dot dA, oh, by the way, Q inside here is 5 microcoulombs. Okay, in case you want to do numbers. Oops, what did I do here? Okay. All right, so this is again the same, integral is the same. So E times the surface area of this sphere, which is 4 pi r squared. Okay. So, and that is equal to, again, charge inside divided by epsilon naught. And now what is the charge inside this Gaussian surface? It's minus 8 microcoulomb plus 5 microcoulombs, minus 3 microcoulombs. Okay. And charge, so the charge inside is minus 8 microcoulomb plus 5 microcoulomb minus 3 microcoulomb. Okay, so for R greater than 8, the electric field is again K Q inside divided by R square, where Q inside is minus 3 microcoulombs. Okay. All right, so let's go back to the diagram and summarize it again. Okay. So actually, let me do it over here. I will draw a neat diagram here again. All right, so here's the charge distribution, and you want to find the electric field everywhere. The electric field inside the conductor is 0. Outside in this gap, what is happening? This is acting like a point charge. The electric field everywhere here is like that due to a point charge of 5 microcoulombs. The electric field here is 0. The electric field outside here is as if this entire thing was a point charge of charge. This is 5 microcoulombs minus 8 microcoulombs. So outside here, this entire thing is acting like a point charge minus 3 microcoulomb point charge. Okay, so that's electric field. Yep. I'm sorry? This part? Okay, so for this part, what we are doing is we are finding the electric field in this region. R, this is 4 centimeters, this is 6 centimeters. So when R is between 4 and 6 centimeters, we are finding the electric field in that region. Yeah, if you want. Yeah. So then we are finding the electric field outside there. This is 8 centimeters. Any point outside this outer shell, any radius. So that this expression gives you the electric field. Oops. This expression gives you the electric field all the way to infinity. Okay? All right, there's a part B to this problem, and what I'll do is I'll just give you the answer to this. So all these arguments were when these two were concentric. So when they're not concentric, here's what happens. There's the center of that, and I'll exaggerate this. All right, so here's what happens. Again, oops. The 5 microcoulomb distributes evenly here on this shell. What you want is here, so what is driving this stuff is E equal to 0 in here, E equal to 0 in here. So we'll write all of that. E equal to 0, oops. E equal to 0 inside, E equal to 0 here. And so what will happen is there will be more, you'll still have minus 5 coulombs distributed here, except that the charge is denser here than there, and then you get minus 3 coulombs distributed outside. So this is minus 5 microcoulombs and minus 3 microcoulombs. Okay. So again, we're trying to find the electric field everywhere. Electric field here is 0. Electric field here is 0. Okay. And the electric field here in this region, the electric field is, so in this region, the electric field is, okay, so we'll call this R prime. So the electric field there is equal to K Q divided by R prime square, where Q is 5 microcoulombs. Okay, so in this region, the only thing that's effectively producing electric field is this. So, but you have to be within the shell. Okay, so r prime is any distance within the shell. And I can't write a range for r prime because here, by the way, so this r prime has a smaller range here and r prime has a bigger range here. Okay, but anyway, so that's only this charge is producing the electric field there. And for r, for and well, what we'll do is for the outside region, we'll measure r from here, from the center of the shell. For r greater than 8 centimeters, the electric field is kq by r square, and q is minus 8 microcoulomb plus 5 microcoulomb. It's equal to minus 3 microcoulomb. Okay. So once you're outside the shell, what we are saying is it doesn't matter what's happening outside. All that is shielded from you. The electric field is just due to this minus 3 microcoulomb that's evenly distributed outside. Okay. So again, so what is happening is with this thing off center, there are more negative charges here, but the negative charges outside are evenly distributed. And so if you're outside, it doesn't matter where this aluminum sphere is inside. You're not seeing the effect of that anywhere outside. Okay, all that is shielded. So, okay, so that's how charges distribute. All right. Oops.